All right, here's some helpful math tricks that you should just know for to make calculus easier and impress your friends. First, here's some common mistakes with fraction bars and some things you can actually do, like legally. So here's a common mistake: canceling something that's not in every single term. Remember, terms are whenever you have a plus or minus. If you have just times in, then yeah, stuff can just cross off. Many things have been canceled this spring. Bummer. Here's some things that'll never be canceled, though. Prayer, you can always do that. Scripture, it's eternal, never passes away. It's always good, true. God's love. Pink Shirt Friday from Mr. Gorbold. Fond memories, you can always reminisce. Nobody can take that away. Encouraging messages to your friends or enemies or whatever, but sending in a note, you can't stop that. Smiles, even in hardship. The A in this expression, A over A plus 2, yeah, that can't cancel. Never should. How about the cosine squared here? This was from our worksheet, and a lot of you tried to just cross off this cosine squared. No. Then that should never cancel. Not directly, maybe if you did some other trickery, but not as is, because you got this minus 1 and this minus cosine. And there's not a cosine squared in every single term, therefore, it cannot get canceled out. Down on this next line, though, this, legally, you can cancel this x because it's in all three terms. See, there's an x, and there's an x in this term, and there's an x down here. There are three kind of terms within this. I just did air quotes, but you can't see that. Within this one fraction. And so you can cancel the x. What you're technically doing, right, is factoring out the x on top and bottom. Oops. It would help if I did that correctly. This is what you're technically doing. That's a 3. And now, this x can cancel. However, you could kind of shortcut that, and you could just say this cancels, this becomes a 1, this becomes a 2, and that leaves me with 1 minus x all over 3x squared. And then don't keep going and don't go x and x cancel. No. That's then now illegal. So that one, sure. This next one, you could take a 2 out, right? Because there's a 2 everywhere, and this one became a 2. And then maybe just rewriting it so it's clear, this is now x minus 1 over 2x plus 1. And then, now this next one seems like if you did that again, that would be illegal because 2 doesn't go into 1. This would actually probably be worse, but you can legally say this is the same as x minus 1 over 2x plus a half. You could still take a 2 out of 1. It just becomes a half. Now, usually that form is worse and less preferred because you don't want fractions inside of fractions, but I mean, you can do that as long as it's everywhere. But you can't just be like, oh, this is x over 2x. Moving on. Well, no, you have to do it everywhere whenever there's a minus or a plus. Okay, another thing that people mistake is to move individual negative exponents when there's a plus or minus. Here's some legal moves. When you just got a bunch of times, then sure, you can simplify this down to, you can move that to the bottom, so x squared. There was already an x down here, so I could make that an x cubed on the next step. And then this y to the negative 3 can come up here as y to the 3. Totally legal. And again, you can make that x cubed on bottom. Here, sure, the 4 note is not, there's no parenthesis here, so that 4 has to stay, but so I don't need a dot. But the x squared can go to the bottom. There was this down here. Now, if I just stick the x squared here, that's technically wrong because I need whatever was on bottom is now going to be times by x squared. And then I could distribute that if I want, but that's fine. That's legal. I could do that because the top just had one term. If the whole, there's kind of two terms on top, but actually not really. The parenthesis combines them into one term. And so over here, I can move that one term, the x plus 7 quantity, negative 2 now becomes 2 because I moved it. There was an x down here. And then what's on top, you can't leave nothing on top, so you put a 1 because I moved it. So that's legal. And then you could distribute that through. Don't make that mistake, though. This does not become x squared plus 7x, quantity squared. No, you have to do the squared first. And I didn't even put it on here as its own rule, but x plus 7 squared, this is the most common math mistake in the history of mathematics, does not equal x squared plus 7 squared. I'm sorry, some of you just really want that to be true, but it ain't, because squaring means multiplying by itself, and when you multiply x plus 7 by itself, you have to FOIL it, and you get x squared plus 7 squared, but there's this middle term of 14x that people miss. So, anyway, that was, wow, bonus right there. Okay, so here's some not legal ways to try to move negative exponents. And so this first one, you cannot equals, no, just to warn you, this is not legal, to just move this y squared up here. Oh, but I used parentheses like you taught me. No, because of this plus sign. And similarly here, you can't just be like, oh, this is the same as 1 over x squared plus y squared, so I could flip that and say, so this is x over y minus y over x times x squared minus y squared, because I'm flipping it from the bottom and it comes up to the top. I meant to have that be a minus, whatever. No, just no. I will show you how to simplify those using one of my favorite tools, Lick 'em over Lick 'em. That's down later. I'll actually go back and do those same two problems in a way you can legally mess with those, but not like that. Okay. Next, trying to split a fraction into multiple fractions when there's more than one term on bottom. So this first one, as I just covered, that x never just goes away. But also some people, so this is no, some people might, instead of canceling the x, say this is the same as x over x plus x over 2. No, it is not. However, yes, this one is x over x plus 2 over x, not x over 2. Because if you had the expression I now have, this expression has common denominators, so I could keep the denominator, add the numerators, and I get x plus 2 over x. So as long as the bottom is a single term, you can do that. So this next one is not x over x plus 3 over 2. No. However, you could, if you really wanted, you could still manipulate this. You can split this up as two terms with an x and a 3, but they have to both be over that entire bottom, which in this particular case is probably not something you'd ever want to do, but you can do that. That is legal as long as you take the whole denominator with each term, not just part of the denominator. You cannot split up a two-termed denominator with a plus or a minus. And so this next one, similarly, cannot get split up currently because there's a minus down here in the denominator. However, if I rewrite this using my Pythagorean identity, whenever there's a squared, it can change into a different one. In fact, 1 minus cos, that's just a clever form of sine squared hiding in there with his Halloween costume on. And now this can be split up into two fractions if I want. And so if I split that up into two fractions, I think I need to move my paper up a little, that would then become sine over sine squared minus 1 over sine squared, which is also known as sine over sine squared is 1 over sine, which also is called cosecant, And 1 over sine squared would be cosecant squared. So that's cool. Which also, you could then factor out a cosecant, although I don't know if I'd want to. Depends on where I'm supposed to go with this. But that's kind of nifty. Little trick there. Yeah. Okay. So those are some don't do those, or do those, but correctly. Okay, next one. Crisscross applesauce to combine fractions. So 3/5 plus 1/4. You have to get common denominators, all that. But there's a faster way if you just did. So to get common denominator is going to be 20. So I'm going to have to multiply this by 4 over 4 and this by 5 over 5. And then I get 12. I get 12 twentieths plus 5 twentieths is 17 twentieths. Okay, I mean, that's not hard. But slightly faster is just to crisscross this. So a shortcut of what I just did, I could just go right across here, is going to be 12 plus 5, and then it's just going to be over straight across 20. And there's my 17 twentieths. But that you could pretty much just do in your head. Let me show you that again. So this one, it'll be 20 plus 3 over 30. So 23 thirtieths. And it's the same as getting common denominators, but it's a much faster way. And this would work even if this was a minus, then this would just be a minus, and it'd be 17 thirtieths. Try another one. A third plus, okay, now this one, normally this should just become 2/6, and the answer should be 6/6. But this crisscross applesauce still works. This would give me 6 plus 12 over 3 times this, which is 18, which is still 18/18, which is 1. So even though that one, you don't have to actually change both of them, crisscross applesauce still works and is faster and fun. More funner, yeah. Okay, so this 2/3 plus 5/4. So crisscross applesauce says this should be 8 plus 15 over the combined, that's not 32, that's 12. So 23 twelfths. Done. Okay, now this would be the same thing, but it would be crisscross applesauce 8 minus 15 over 12. So negative 7 twelfths. Just a quick reminder while we're here. So 2/3 times 5/4. Is that the right numbers? Yeah. You just multiply straight across, or you can cancel anything because there's no plus or minus. So now I can cancel, make my numbers a little bit smaller before I deal with them. Okay, just doing some quick review here. And then divided is, I like to say stay, change, flip, is my little, I don't know what you can call that, my little saying. So if I had this and I am dividing it by, what is it, 5/4, then the first one, this one stays, the divide changes, and the second one flips. Stay, change, flip. And so now, and then whenever you're multiplying, you just go straight across. And that one didn't cancel. Nothing canceled first. So just a quick review of fractions. Wow, that's really tiny now that I zoom back out, but whatever. Here's a useful crisscross applesauce in a trig proof. If I just change the left side to sines and cosines, sine over cosine, and this would be cosine over sine, equals, I'm not going to change that, I'm just going to draw my little line down here. Now over here, if I just do my crisscross applesauce, this needs an extra sign, so this becomes sine squared. This would go up here, so this would become cosine squared, and then the whole thing would be over the times those together, which I'm going to rewrite sine cosine rather than cosine sine. Actually, I should have left it the other way because of how the answer is written, but whatever. And now, hopefully, you are starting to get used to trig identities, and you see sine squared plus cosine squared, and you always know that that's just 1. And then over sine cosine. And now, oh, hey, let's use one of our other rules. I didn't actually fully do this one, but this could be split up as one, like you could split this up as kind of two different fractions, because 1 times 1 is still 1. And now this becomes cosecant and secant, which I switched the order, so now they're in the wrong order, but I'm going to go ahead and put my check mark because now my left side matched my right. So there's a crisscross applesauce. Save you some time and probably would impress your friends, perhaps even earn you the favor of a significant other or a future significant other. Okay, my favorite, lick 'em over lick 'em. LCM, least common multiple over least common multiple. Real quick, a complex fraction that's just what we call it. Whenever you have a fraction somewhere within a fraction, like all 5 of these examples, the 6th one doesn't have anything right now, but when we rewrite it, it'll have a fraction and a fraction. And the 2 down here are the ones from earlier that we tried to cheat on and realized, yeah. Problem with having a complex fraction, they're hard to work with, and a complex fraction is too great of a temptation for many students. It would be better to transform the fraction into a more recognizable form. This is a good life lesson, right? If you would just see temptation for what it is, you could stand up against it, right? If you saw that doing such and such thing will lead to such and such thing, you probably wouldn't do it, but in the moment it seems innocent, it doesn't seem like a big deal, and you take the bait, and then, oh man, when desire takes root, it gives birth to sin, and sin, when it's fully grown, gives birth to death. It's biblical right there. Well, these, prone to all kinds of like, oh, there's X's here, I'll cross them out. No. Definitely. No. Cannot do that. But once you get rid of these complex fractions. Okay, now, the standard way to do these problems over here on the left, this first one, is already kind of in the form you want. And we could do the whole stay, change, flip, which here, so this thing would come up here flipped. So it'd be 6y over x squared. And that will work. I'll go ahead and finish the problem. 6 over 3 can become, let's see, the y's will go away and this become 2 over 1. Here this x goes away and this becomes x to the first. So I'd get 4x to the first. Cool. But another way to do that is simply to take any denominator within the denominators, of which there's 2, a 3y and a 6y, find the least common multiple of all of those, which in this case is 6y, and just multiply the whole thing by 6y on top and 6y on bottom. Now this is perfectly legal because I'm just multiplying by a clever form of 1, which we'll talk about later. But what this does is auto clears all the fractions. And so this 6y will automatically, every single time, cancel out that 3y. In this case, I'm left with an extra 2. So that is left with a 2. And then I'm just going to go ahead and copy the 2x cubed. Now the top has no fraction in a fraction. The bottom, if I times it by 6y, completely goes away. And it has no fraction. And then this simplifies to my 4x. Now in this one, that didn't necessarily seem faster, but that's because, this one was already set up perfectly for the other. This next one, the standard move is to get the top as a whole. So I'm going to go ahead and write on this, but then I'm going to just erase this and do it as lick 'em over lick 'em. So maybe don't even write this, just watch. Normally what you have to do is say, okay, this needs to get to be x over x. That way the whole top becomes x plus 1 all over x. Then on bottom, this is missing an x squared, so I need to rewrite it like that. That way the bottom can become x squared minus 1 all over x squared. Now I can take this and flip it. It becomes x squared over x minus 1, squared minus 1, and then I can somehow simplify that and keep going. Now I don't want to do it that way, so I'm going to erase all that. And instead, I'm going to do lick 'em over lick 'em. So within this, there are 2 different denominators within these fractions. One is an x, one is an x squared. The least common multiple of that would be x squared. So if I take this whole top times by x squared, and the whole bottom and times by x squared, should probably use lots of parentheses, all of the fractions will magically clear. So x squared times 1 is x squared, but x squared times this is simply x. Now on bottom, x squared times 1 is x squared, minus x squared times this is just 1, it doesn't go away, and now I have a much faster and easier form of that. Now this actually, with some cool tricks, can still simplify a bit, because this is x and x plus 1, and this is x minus 1 and x plus 1. And so this actually can reduce down even more down to this, because those x plus 1s go away. Which, if I kept going with the other method, would still work, but this way, so much quicker and takes less space on your paper. Double bonuses. Let's go straight to lick 'em over lick 'em on this one. Hopefully, with enough of these examples, this will become much more intuitive. In this one, I have 4 fractions, but all of them have an x, so the least common multiple needs an x to the first, and the least common multiple needs 1, 3, and 6 all go into 6, so if I multiplied everything by 6x, all of these fractions will magically disappear. The key is I have to lick them over lick them. I have to do it on top and bottom, or else I've completely changed things. If I multiply by top and bottom, I'm not doing anything. I'm just timesing it by 1, but it's going to give me a form that's much easier to work with. So 6x times 2 over x is just times it by 6, so 12. The 6x here is going to cancel the x. The 6 goes into 3, so this is need an extra 2, and there was a 2, so it becomes a 4. This is also known as 8. Okay, on bottom, 6x times that is just 6, and that 6x completely goes away, and so I get 8 over 1, so 8. So the whole thing was just 8 in disguise. Okay, let's go back to this guy. Does not look, wow, that's pixelated. We could still read it though. So this is the same as 1 over y squared right here, which now you can't just move that to the top because of this plus is ruining the party. But I could take this, if I want to just clear that, if I times the bottom by y squared, that will go away. However, I can't just times the bottom by y squared. That's highly illegal. But what I could do is times this by y squared over y squared, lick 'em over lick 'em, and that gets me, I could either distribute the top or leave it. I don't know which would be better. I don't think it really matters. I'm going to distribute it. So this would be y cubed plus y squared. Then the bottom, and this is the whole point of doing this, I now get xy squared, but now just plus 1, because the y squared canceled. And that is equivalent, although much higher resolution, to my original, except now I don't have a fraction in a fraction, which I didn't before, but I had a negative exponent in a fraction, which is the same thing. And so those two are equivalent, but maybe this one on the right is going to be easier to work with for other reasons. And similarly, here, I see a fraction in a fraction, but really this is the same as 1 over x squared minus 1 over y squared. And so now I have 4 fractions within fractions. I have 4 denominators, a y and x squared and a y squared. Well, if I multiplied everything by x squared, all the x's would go away, and if I multiplied everything by y squared, all the y's would go away. The least common multiple of x, y, x squared, and y squared is x squared, y squared. So if I times that through on top, it will magically clear those fractions out. So x over y times x squared, y squared would give me an x cubed, right, because I had an x squared and an x, and the y squared and the y would become just 1y. Then this would become, similarly, this would be y cubed, and the one of the x's cancels, so this would be xy cubed. And then on bottom, now I get x squared times 1 over x squared is 1, but then there's the y squared, so this becomes y squared, and then minus x squared. And perhaps I could do something there, perhaps not. I don't actually know, so I'm just going to leave it. But that form is the same as the original, but that one's probably going to be much easier to work with. I can see all kinds of different things now. So that's lick 'em over lick 'em in several cases. And then we also use this. This was from our worksheet. This doesn't have any fractions in fractions, but it does once you do your first step, which is 1 over cosine minus 1 all over sine over cosine. Oh, this was not exactly like one from the worksheet. Plus 1. If you were to do that for reasons unknown, probably because there's some other thing going on in this problem, as of now, there's nothing wrong with it in its form. But if I were to do this for some reason, now I could just take this times cosine. That was supposed to be a parenthesis. You don't even have to put the Lickum in parentheses. The key is to have this in a parenthesis so you don't forget to distribute it through. And now this becomes cosine times 1 over cosine is just 1. So that's just 1. It's kind of working down here. Minus, now I'm timesing through the cosine, so that becomes cosine. Now on bottom here, sine over cosine times cosine is just sine. The cosine canceled out. And then plus, and again, this 1 becomes a cosine. And so now, now I'm there. And now, now I can just, hey, cosine over, no, don't ever do that. Stop. Oh, my goodness. See above, right? Now, that's all I can do. Is that better than the original? I mean, not really. They're but they're the same. And if this was a trig identity where I was trying to get to, say, this or something else that had sines and cosines, these would be valid steps along the way, Lickum over Lickum. Okay. Other times, we do what we were just doing, multiply by a clever form of 1, because as long as you multiply by something over itself, you're not changing the problem. This is helpful when you don't have an equal sign. If you have an equal sign, you could potentially just times a denominator over to the other side. But when you don't have an equal sign, you can't just times it by something for convenience sake. Like here, this is called rationalizing the denominator. I don't like a square root of 2 on bottom, but if I just times it by root 2, now root 2 times root 2 is just 2. Huzzah! So 1 over root 2 is the same as a half. Well, no. You have to, whatever you do on bottom, you have to do on top, right? Well, what did I do here? I just multiplied by 1, but in disguise as root 2 over root 2, and I get this. Why do that? Well, because it's just a general rule is you're not supposed to have radicals in denominators. So that's just sort of, a rule. There's nothing wrong with 1 over root 2 necessarily. But you've already done it. That's multiplying by a clever form of 1, but you called it rationalizing the denominator. Here's another one. I don't know if you remember how to do this, so I put it on here. This one, to rationalize this, you have to multiply by its conjugate, because then this is a difference of 2 squares, which should just be that, which it is, which is also known as 1 minus 5, which is also known as negative 4. So the bottom just becomes negative 4. But whatever I did on bottom, I have to do on top. So what I'm really doing is multiplying by a clever form of 1 called 1 minus root 5 over 1 minus root 5. And then I could distribute that and I get 3 minus 3 root 5. And then that's sort of the final answer. Sometimes this negative 4 can cancel those a little bit. Not in this problem, I would say, obviously. Okay, here's a neat little trig identity that normally we would just start going on the left side. We'd switch it to sine over cosine and 1 over cosine, and then stuff is going to happen. But let me show you for no reason at all, but because we can. Here's another way to do this. I'm going to multiply this by, check this out. Sine x is supposed to, normally we take the more complicated side, the left, and make it more simple, the right. But you can do it this way. I know that somehow I need to have a secant on bottom, so I'm just going to put a secant on bottom. But that's not legal unless I also put it on top. And so now my goal is to turn, now that the denominators match, I now have sort of a separate trig identity. Now my whole goal is to show how do you get tan x to equal sine x secant x. And I just kind of took the denominator out of the equation. Oh, well, this is just 1 over cosine, which is then sine over cosine, which is then tangent. So this could be rewritten as sine times 1 over cosine, put my x's in, over secant. This is getting a little jumbled, and then that equals tangent over secant. And check, because that's what the left was. So that's like a different way to do it, is to make things more complicated, but strategically, because I see a secant in the denominator, so this one I'll just put a secant in the denominator. It's like changing to get common denominators, right? So I could apply that over here in a really cheating way. I could just say, well, this is missing a cosine. Oh, there's a t, whatever. Not anymore. I don't like UT. And so I need that up here. And this one is missing the 1 minus sign, so I'll just stick that over there. And now that the numerators match, my goal is just to figure out how can I make cosine squared be like 1 plus sine. How does 1 plus sine, 1 minus sine turn into cosine? This is getting really messy, sorry. Alternatively, I'm not going to do that problem like that. Alternatively, in blue, I'm just going to write over myself, I could take this times, I need a 1 plus sign on top, so what if I just put a 1 plus sign, or was in the spirit of multiplying by a conjugate, because the bottom then becomes, sorry this is so messy, but 1 plus sine x times cosine x, again I'm just switching to x. I'm not even going to touch the right side. And then over 1 plus sine, 1 minus sine, but 1 plus sine, 1 minus sine is 1 minus sine squared, and 1 minus sine, and this is over the top, 1 minus sine squared is cosine squared. Oops, okay. And then that's all over 1 plus sine x and cosine. And now, but now the cosine and the cosine squared do cancel because I have the parenthesis. There is a plus here, but I'm taking the whole parenthesis. Is just being times, so I can cross that off, and now I get 1 plus sine x over cosine. Sorry if I kind of went through that one like super fast, but which now matches on the right, check. So there's a multiply by a clever form of 1, because I was kind of stuck. I can't switch everything to sine and cosine. It already is. There's no squareds to use Pythagorean identity. Oh, but if I have a sine plus 1, if I multiply it by sine minus 1, or in this case 1 minus sine, I can multiply by 1 plus sine, and that'll become 1 minus sine squared, which is also known as cosine squared. So that was a bit tricky and super fast. But I still have one more thing I wanted to do. And this is already a really long video, so apparently, yeah, whatever. Okay, factoring out the least power. This will come up in the middle of the year of calculus and confuses students. I'm not going to super thoroughly teach it, but hopefully this little intro will save us some time next year. It's a great little trick. It's obvious here. You could do this one, no problem. Factor this. You say, oh, there's an x squared in each term. The least power of the base x is x squared, so I could take out an x squared. What's left? 1. Don't make it go away, right? And then there's still an x squared here. There's still a 2 and still an x, and I'm done. Well, the place that will be helpful in calculus is when you have negative powers. What I'm technically going to do here, I'm not going to do it like this, but I'm going to write it like this real quick. This is the same as this, and so what I could do is get common denominators if I want to simplify this. Common denominators, this one is missing an x, and this one is missing the x squared, and this one has everything, and so I could rewrite this as x minus there's no 4. Minus x to the 4 times x squared is x to the 6 plus 2 all over x. Like I could get that all as one big fraction. Now I don't know if I need to do that or if that's helpful. But a different way, here's the point of this rule. It's a shortcut to doing that. It's to say I'm going to take out the least power. In this case, the least power is an x to the negative 2. So I'm going to factor out x to the negative 2. But there is no x to the negative 2 in these other terms, you say. Well, there is, but it's hidden. So x to the negative 1, if I took out an x to the negative 2, what I'm doing is dividing that. X to the negative 1 divided by x to the negative 2 is, subtract them. Negative 1 minus negative 2 is positive 1, so this first term becomes an x to the first. The next term, if I took x to the 4 and divided it by x to the negative 2, 4 minus minus 2 is 6. So this would be x to the 6th. That's what I had right here. That's just taking this, and I'm factoring out this. How do I factor out something that's not there? Well, it is there. It just becomes more. And then the last one just goes away. And now I have essentially this, but in one short step. I showed some work down here, but that was actually mental work. I just wrote it. And so this becomes like a shortcut. What's the point of that? And then this could be rewritten as like 1 over x squared if you wanted. 1 over x to the positive 2 if you wanted. The point of that is, what if this whole thing was like equal to 4 or something? Or better, what if it was equal to 0? how do I find the zeros of this? Well, once I factor that out, now either this is 0, which is never true, or this is 0, which is maybe something I could work with. Whereas initially, it's all complicated looking. Where we're really going to see that in calculus is with radicals, and this is going to be real advanced here. But the least power of x remember, this is an x to the half in disguise. The least power is x to the negative 3 halves. So if I take on x to the negative 3 halves, oh, maybe I should have done one where they also had like a 2 in common, because you could take a 2 out with it. That's going to leave a 2 x to something plus minus 3. That minus 3 is actually already done because I took out the x to the negative 3 halves. But here now, okay, so if I have x to the half and I'm dividing by, because that's what happens, you take out x to the 3 halves, this would be 1 half minus 3 halves. Well, check that out. That's cool. That's 4 halves. That's 2. So this becomes an x squared. The middle term, x to the negative half over x to the negative 3 halves, that's x to the negative half plus 3 halves. That's the same as 2 2's, which is just x. Wow! That's super cool. So when you have these weird radicals, now the weird radical just becomes one thing, but the rest of this now is just simply a polynomial, which I could then factor a quadratic formula or something depending on what I'm actually doing in the problem. I could then work with that, and this whole radical that was messing up all my terms just becomes its own little problem as its own separate thing, but now I can work with the rest of the problem. So that's kind of a really nifty shortcut that we'll do in the middle of the year in calculus. And I'll review it then, but hopefully it'll sink in. So, tricks to impress your friends or family, right? Because that's probably all you're around. So you could, go show them, hey, Mom, check out my cool math trick. And your mom will be like, wow, you're so special, dear. I love you so much. You guys are loved, and I hope that you're now slightly smarter even than you were before this video.